Always so loud. Um, yeah, so hi everybody. It's my pleasure to introduce to you today's speaker, Dr. Michael Cohen. Michael is currently working as an assistant professor at Armhurst College and a research scientist at the McGovern Institute for Brain Research at MIT. He completed his PhD at Harvard University with Ken Nakayama and George Alvarez, after which he did a postdoc with Nancy Kanwisher at MIT. He currently investigates the limits of perception, memory, and cognition using a combination of neuroimaging, psychophysics, and computational modeling. And today he will talk to us about the resolution of perceptual experience. Over to you, Michael.
All right, so I really can't stress enough, please, please, please do not hesitate to interrupt me. It will give me a chance to have a sip of coffee or water. So if anything I say even remotely is unclear, you want to hear it again, you just have a clarification question, not only would I say like, don't hesitate, but I would actually kind of encourage you, please interrupt me. So it's great thanks for the invitation. It's great to see a lot of familiar faces. I think that probably I can just dive in. A lot of you all have maybe seen this opening slide that I use. It's kind of my go-to opening slide, but this is an image actually from my lab when I was in grad school over in the Vision Sciences Laboratory in Harvard. And it was kind of a weird little waiting room. We had bottles of champagne for when you got your PhD. We had these like big spiral things that we would sometimes do motion after effects with people. We had and janky old desktop monitors. And the reason that I am showing you this image is not because I want you to know about how quirky and fun we were back then, but actually because while this image has been up on the screen, I changed a lot of things. So over the last 20 seconds or so, this image changed in a variety of ways. So this is not the first image you saw when I first put it up. The first image you saw looked like this. And over the course of about 20 seconds, I changed it to look like that. Oh gosh, not like that. Well, okay. Sorry, my keyboard is giving me a little difficulty. So hopefully you probably noticed some of the things that are changing in this particular image when it was happening, but you probably didn't notice all of the things that changed. So here's another demo. I stole this from, I think, a European car commercial I found on YouTube. I just made it into a keynote thing. So this hasn't started yet. I'm going to change a bunch of things once again. It's not a gradual change blindness one, though. This time it's going to be kind of more of a standard flicker ones, except in this case, it's going to be the type of situation where once it changes, it doesn't change back. So it's not going to be alternating between like picture A, B. So I'll just tell you something now, for example, that this large van here is going to turn into a small black car. So pay attention, see if you can catch some of these. My guess is you'll catch some of them, but my strong suspicion is you won't catch all of them. So let's try it out. So like I said, that van in the bottom right is going to change to a car, just like that. There's a couple of other things that are changing. I don't know how well my voice and the slides are synced up, so sorry if there's a little lag between what I say and what you see. So we're almost done. And my guess is if I asked you all, did you notice any changes? A great many of you would be able to say, yes, no problem. But this is the final image, and compare it to the first image, which looked more like this. And over the course of about 8-9 flickers, it changed from this image to that image. And so it really was a comfortable majority of the images or of the pixels that changed to the sky, all the facades of the building. There's a nice little homage to the invisible gorilla up there. And I'll just do one more demo that actually I found in an advertising for dental floss. So it's an advertisement for dental floss. I realize this is very random because the whole point is like, oh, if you have something in your teeth, it can ruin an otherwise lovely picture. Again, handsome couple. This guy needs some dental floss from Colgate. Last couple there. But the real reason that I'm showing you this is that one of the main points of this is that it shows that when food is in your teeth, it can draw attention away from other more salient visible defects. So for example, on this woman, she has a 6th finger that you may not have noticed. This man is missing his right ear. And then this last one on the bottom, I like the best because it's a little creepy because you have to ask yourself, whose hand is that? But my guess is a lot of you didn't notice these things across these 3 different demonstrations. And the one thing that they all show and suggest is that perception of the visual world might be extremely limited, or at least counterintuitively limited. And this is consistent with results that people have done over the years where they've tried to estimate the capacity of attention and working memory, and they have found that it's limited to more or less around 4 items, give or take a few more. But this is a bit of a paradox because no one has the impression that perception is as limited as these results that I've just been showing you or these prior results might suggest, because for example, when I'm showing you an image that looks like this, whatchamacallit, this waiting room, I don't think anyone would say that this visualization here does a good job of capturing your phenomenology. It's not like you see 4 items in the world and then the rest of the world kind of fades to nothing. But at the same time, it feels like we have a much richer and broader sense of the world around us. But again, these demos that we just looked at were intended to provide us with good reasons to be somewhat skeptical of those intuitions. And so a fundamental question that I'm personally interested in is, why does it feel like we see so much when the data suggests we see so little? I can't emphasize enough, this, as I'm sure most of you know, is a super controversial topic. There are entire symposia at ASSC, it seems like almost every year, kind of centered on this particular question. It's really, in my opinion, one of the fundamental questions in consciousness research, which is basically, just to put it more simply, is how much of the world, in this case, the visual world, are we actually aware of at a given moment? Because, okay, we might say it's not this sparse, but there's a lot of empirical data that says it's not quite this rich. So then what does the resolution actually look like? And that's really what I'm going to talk about today, is just trying to figure out what kind of image should go on a slide like this. In other words, can we capture and quantify the exact richness of perceptual experience? And so the logic behind all my experiments is pretty simple. Across all these studies that we're going to do today, I'm just going to ask this question of basically, how much of the world can I alter before people will notice? Okay. And the logic then is that if we alter the world and people don't notice, then those things that I altered or I took away or I changed, they must not be part of your perceptual experience. And I totally am aware that there are, issues about, well, maybe you saw it but forgot it. But for right now, just for simplicity's sake, this is sort of the simple way to talk about the logic. So what I'm going to do is I'm just going to take natural scene images and I'm just going to kind of start stripping away at them and seeing when do people start spontaneously noticing, like, wait, you did something odd here. And so I'm going to do this using 2 broad methodologies. One I call a snapshot of perception, which is just my way of kind of summarizing, good old-fashioned psychophysics. But then in the last third or so of the talk, I'll tell you about some work moving this into what I call immersive perception, where we do experiments like this using gaze contingent virtual reality. And so these are going to be the 2 kind of approaches I use. And then the 2 dimensions that I'm going to talk to you about are going to be things like natural image statistics. So when I say altering the world, I mean taking an image like this guy sitting here, having his lunch, and alter it in the sense of, distorting the peripheral statistics while still preserving certain aspects of the natural scene. And then the other dimension will be in the domain of color, where you can take an image like this, and if someone's fixating at this mermaid's face, you can remove all the color from the periphery, you can rotate the colors of the periphery, and then the question is just going to be, at what point when you start changing the world like this do people start noticing? So let's start over here on the left with stuff regarding this idea that I talk about as a snapshot of perception, because I wanted to start a little simply and just ask, how much of the world can you see in just a single glance of the world? So this is not dealing with anything like prior knowledge or memory or familiarity. We will kind of get to that in a little bit. So for right now, it's just in one glance, what is a sort of snapshot like you could capture with a camera? And so to do this, when we started out, we needed a way to alter the world in a principled manner. We were looking for a dial that we could kind of turn that allows us to increase or decrease how much we alter the world. And so what we did is we started with this algorithm by Jeremy Freeman and Eero Simoncelli. And the way that this algorithm works is it's intended in crude ways to sort of mimic retinotopy, in the sense that you take an image and you put all these pooling windows all across this image and the reason I say it's kind of like retinotopy is because they get progressively bigger and bigger as you go out into the periphery. And what you do then in terms of each one of these individual pooling windows is you measure a series of statistics to get the sense of like, what are the different, natural scene statistics in each of these little regions. And then once you have those measurements, what you can do is you can take an image and you can distort it to preserve some of these measurements that you've just taken. But as you can see, it makes the image look a little scrambly, a little different, and so on and so forth. So in this case here, the baby's face is pretty much untouched, but the further you get into the periphery, the more distorted it gets. So let me just show you a few more examples of what this looks like. If you're imagining, because this has been modeled with the idea that a person is fixating on the red dot, you can see that out in the periphery, it gets more and more distorted. In the periphery, it gets more and more distorted still. Okay, and so the reason that I say that this is like a dial that you can turn is because what you can do is you can take those pooling windows and you can change how big they are. And the bigger you make them, the more you scramble it. So if I have, say, a starting situation like this with relatively small pooling windows, I can just turn a knob, make these pooling windows much bigger. And like I said, what happens is an image that initially looked like this now looks like this. And if you compare these two images, you can start to see that, like, yeah, before you were able to see this guy to a certain extent. But then once I go back to the more scrambled version, you can kind of make out the horizontal stripes in the back of the dog. But now the guy, except for his arm here, is pretty much completely gone. Here's some other ones. This baby again, if I turn the knob a little bit more. Little kid, if I turn the knob a little bit more. And so these are just hopefully giving you a sense of all the ways that you can do this. And then the final thing that you can do actually is you can even take this algorithm, you can take just one of these pooling windows and you can make it the size of the entire screen. And when you do that, that's where you get maximal scrambling, where really you don't get any of the objects or any of the like contours of the natural scene. So in a situation like this, though, when you're looking right at it, you're not really seeing anything. And so what we would do is actually we would take this image as our most distorted scene. And what we would do is we would kind of preserve this foveal region in the middle from the original photograph. So in this case, it would be, this dog and this little toy cannon, and then we would just place it on top of it. And so
Question,
even though
Michael.
Yeah, go for it. What's up?
Could you specify a little more what you're doing when you say scrambling? What are you preserving and what are you destroying?
Yeah, so you're basically taking a lot of measurements about things like spatial frequency distribution, orientations, brightness, luminance, contrast, cross correlations, like really just good old fashioned image statistics. If you think of, Ruth Rosenholtz, Ode Oliva, Antonio Taralba, Jeremy Freeman, Eros Micelli, it's just kind of the basic sort of thing so that you have this sort of general, you're not getting an image that's wildly brighter or, has a lot more vertical energy or something like that. So it's pretty basic sort of image statistics that, have been around since around 2000.
But the joint statistics of various kinds are being destroyed or being altered.
Yeah, they're being altered. So what ends up happening is that once you scramble it, the model that after you've taken all these measurements, you basically tell the model, like, take a piece of white noise and start modifying this white noise until it has the same statistics that you just measured in the natural image. So this image here and the original one have the same statistics measurements, even though they look so radically different. And so if you make it a huge pooling window, you destroy a lot of those features. And if a really small one, they get preserved a little bit more. So let me just show you a few more examples of this large scramble. So this would be a case where it's small scramble. Then there's a case where it is a medium scramble, and then again, a large scramble. And we'll just do one more example so you get a real sense of it. This is like a sandbox. One thing I want to point out is when it's medium scramble, you still kind of get the like circular ovalness of the sandbox in this medium condition. But then when you go to the largest condition, even that global structure is kind of lost that you have. Oh no, sorry, there's one more example. These are fun to look at, so we can look at one more example. So small, medium, again, you can kind of make out the door, you can kind of make out that there's something on the wall, this is the table he's sitting at, but then when you go to large, even those sort of global layouts are completely destroyed. So with these images, what we wanted to do is ask, how much of the world can we alter before people notice? So at what point will people naturally and spontaneously recognize that we have done this? So we needed to, in this case, we wanted to give people a really simple task to do when they came in to kind of, hold their attention so they weren't looking for the scrambling. And so what we did is we just would show people some images and we would say, yes or no, did the last image you saw have a human face in the middle? We chose this task, I'm going to be perfectly honest, a little bit randomly. We wanted a task that felt common, and we were like, object recognition, face detection, that's pretty common in everyday life. We wanted it, why in the middle? Because usually people are putting their focus and detecting objects in the fovea. Don't get too hung up on this task though, because I'm going to show you what these results look like in a little bit, where you do a bunch of different tasks, but just for the time being, all it is just face detection. So you could see a wide variety of diverse scenes, and these are all some examples of what target faces, with human faces in the middle look like. So in this case, if you saw images like this, you would say yes. And we actually always put this little red dot right on the face to make it super easy. Here are a bunch of images where there's obviously no face in the middle. And then here actually are some images where there are faces, they're just not in the middle. And so in a situation like this, you'd still say no because the face has to be in the middle. You know, it's a detection task at fixation. And oh, I should also even mention, we sometimes even had, try to make it a little more challenging. We would even have animal faces sometimes in the middle, but people would also know like the answer to this isn't no, an animal face isn't a human face. All right, and so all that would happen is you would see one image right after the other. It would go on for a little bit. And then as soon as the last image disappeared, you would just be asked, did the last image have a human face in the middle? So in a situation like this, you would say yes, because on the top right, you can see there's a little face. In a situation like this, you would say no. And just real quick, for those of you who might be interested in, each image was up for about 288 milliseconds and then a 100 millisecond gap. The reason we chose the 288 is because I did a huge thorough survey of the literature about the average length of saccades and naturalistic viewings. There's a wide variety of estimates, but when I just literally took like 30 papers and averaged them together, we got that it's about 288 milliseconds in natural scene viewing. So that's the number we went through. So let me show you what a few of these trials look like. I apologize if this seems a little skippy or if it's not as clear because it's a video trying to play over Zoom. So we'll do our best, but this will hopefully give you a sense of what it looks like. So just keep your eyes here. And then when the last image goes off, I'll ask you if the last image had a face in the middle. So in that case, you would say yes, because there was a guy standing there. Let's try another one. In that case, you would say no, because it was just like an empty bar scene. We'll do one more. And in that case, it was yes, because it was a little boy like in a playground or something. So real quick, I'll just show you how well people do at this task. So it's just how well do people say yes, no face, or no face for these two conditions, depending on what the last image is. And there's just really one point I want you to take home from this. This task is super easy, okay? It's not a super attentionally demanding task. Usually when people do get it wrong, which is like, 1 out of every 10 people, they're like, oh, sorry, I hit the wrong key, or I sneezed at an inopportune time. It's a fairly trivially easy task. It's really intended to not be super attentionally demanding at all. So this is what we would do. You'd come in, you do like 10 trials of that face task, and then we would scramble, for lack of a better term, the very last image. So you would see a bunch of images, and then the last image, as you can see here, has been kind of altered in the periphery, okay? And so it could be this little boy, it could be, this little girl, it could be anyone. And the whole point is just all of a sudden, the last image we're gonna just toss in is going to be one of these scramble ones. So here I'll show you an example of that. The last image in a second is going to be like a scrambled pug. Yeah, exactly. Okay. So as soon as that scrambled image disappears, okay, the moment it disappears, what we start doing is immediately, like we're in the room with a participant, ask them a progressively specific series of questions. We had a little script. So as soon as that trial goes blank and we've shown you the scrambled image, we'd ask them, hey, did you notice anything strange or different about that last trial? If they say no, we will then say, okay, well, if I were to tell you there was something different about that last trial, could you tell me what it was? If they say no to that still, we then say something even more, which is, if I were to tell you that there was something different about the very last image you saw in that last trial, could you tell me what it was? So we're really getting all the way to the moment and telling them, hey, we did do something, to try to just probe them. We'll even basically give them the answer, and we just have to get them to tell us, because we do this because sometimes people will be like, oh yeah, there was like a parrot and I hadn't seen a parrot before. And so we try to focus them and making sure that they notice the thing we cared about. And what we do is we just replicated this a bunch of times with images that are more or less scrambled. So this first result I'll show you is just 3 layers of scrambling. So over here is what we'll call the smallest scrambling, medium scrambling, and then the largest scrambling, okay? And so what I'm going to do is just in a second show you how often people notice these amounts of scrambling, and I'm going to plot those 3 conditions down here on the x-axis. And the data I'm going to show you is how often people do not notice the scrambling, okay? So in this particular case, when I show you a bar like this, what this bar is telling you is that every single participant who came in did not notice that we did the small scrambling. And that makes some sense. It's very little scrambling. It's mostly happening in the periphery. So yeah, 40 out of 40 people are just like, sorry, no, I didn't notice that, okay? When we go to the medium scramble condition, we do get an effect though. We can notice, actually it's like a flip of a coin. It's about 50-50, where exactly half of our participants did naturally notice that we scrambled the images, where the other half were like, sorry, I have no idea what you're talking about. And then even in the largest scrambling condition, interestingly enough, at least to me, it only went down to 48%. I really thought that this was going to go all the way down because, to be perfectly honest, when I looked at images like this, I was like, how could someone not notice this? Like, yeah, you could notice that there's a woman's face, but this is a wildly distorted image. It's very odd. There's no global layout. There's no gist. There's really nothing there. Here, for some people, this image, to me at least, takes a second to even understand what's going on. It's like, oh, it's like a bar, but there's nobody there. Again, little girl, how could this be? People are really not noticing this. And so since my goal was kind of to figure out where the breaking point was, and to get a real sense of like, okay, well, how much do I have to distort it so that people really, really notice it? I actually had to get a little creative, because with this particular algorithm, we can't scramble the images anymore. This is as much as this sort of particular image statistics algorithm allows us to do.
Michael, can I just ask
quickly?
Yeah, no, go for it.
So is there just one critical trial here, or multiple critical
One critical trial. This is a one-time kind of classic inattentional blindness thing, yeah.
But they've already done multiple face detection judgments before that one trial?
Yeah, they do exactly 10 normal trials and then one critical trial. So it's like a 4-minute experiment.
And are they instructed to fixate the dot, or is that just implied by the fact they're told to concentrate on the center?
It's actually just implied by it. If they wanted to move their eyes a little bit, they could. If they wanted to divert their attention to the periphery, they could. Like we were purposely trying not to constrain people too much, besides just giving them a basic object detection test. So yeah, we did not have an eye tracker or anything like that, at least right now.
Was there a distinction? Oh, sorry.
Yeah, one
I
quick
wanted to
question
ask
as
a quick-
well. Do you think some of the size of these effects is depends on the fact that people are used, in fact, now to see images with fabricated backgrounds and I don't know, sci-fi images, etc., etc. So, in other words, are you telling them that the images are photographs or unmanipulated photographs or not, and would you expect the effects to be different?
My guess is if we told them at the beginning, like, hey, we're going to show you some photographs and we're going to manipulate them and alter them in a sort of sci-fi way, that, yeah, the results would change, because in that situation, you are, even though you're not using these words, kind of implying or instructing to a participant, like, hey, you need to shift your attention because we're going to do something different. Like, you're kind of putting them on heightened alert, because even though you're telling them to look for a face, I would argue that their attention is going to go elsewhere, because they're like, wait, you just said you're going to do something odd. And I even have some data I'll show you in a couple slides, where when we give people a different task, we don't tell them exactly what you were just suggesting. When we do give them a different task, it does alter it. And I think that's entirely consistent with just this idea that when your attention is divided or spread out or focused, yeah, that's going to absolutely change the resolution of awareness. So part of the reason that I'm going there is because I do want to make sure to stress that I'm not trying to say this is the resolution of pretension or of perception in all cases. It's just, the resolution, at least in this kind of simplistic sort of situation.
Was there a distinction in the detection of the scramble between the faces and the objects?
Oh, like when you notice, like if you get the last image as a face, do you notice the scrambling more or less than if there's no face there?
Exactly.
No, we didn't find an effect there, but it's entirely possible that we were a little underpowered for that particular question. We didn't find one, but I wouldn't be shocked if actually that mattered, because you're like, oh, look, there's the target. Again, your attention might zero in on the target, in which case you might not notice stuff in the periphery as much, but we didn't see any evidence for that, at least. Okay,
Could I ask you one last question? Sorry.
Yeah, of course, go for it.
I'm just curious about what their report was. Like, what did they say they noticed when you asked them? Did you notice something?
On like for people who failed to notice?
No, the people who actually noticed.
Oh, so
Did they
people who
notice?
noticed, yeah. So people who noticed, like we actually didn't even usually have to do multiple questions. Like 99% of the people who noticed were like, yeah, you like guys did something weird to the periphery. It was like out of focus. I could only see the middle part. Like they immediately got it. And then the people who didn't, usually it's very rare that people got it with leading questioning. And then the people who didn't get it, they would just be like, no, man, like, sorry, I saw a dude's face in the middle. Or they'd be like, wow, like, you could even show them the final thing to show them like, hey, here's what we did. Did you notice this? And they'll be like, whoa, really? Like, no, I had no idea. So it's exactly kind of just a simple it really was a bimodal distribution, just in the sense that some people are like, yeah, you always did something weird to the periphery, versus like, no, man, sorry, you told me to look for a face, so I was looking for a face, I didn't notice it. Okay, so since we can't scramble these images anymore, we had to get a little creative, because I was just literally trying to be like, all right, all I want to know is what the boundary points are. There's any number of ways we could do this, but here are just the ones that I tried immediately that I'll tell you about. So the first thought we had was like, all right, well, what if we take the center part of one image, in this case, this like little girl at, I don't know, Disney World or something, and we put it on a completely inconsistent image. Like, so in this case, like the Matterhorn. So this will be like now our critical image, okay? Or we put these computers in the jungle, or this little boy in a dark forest, or a dog towering in a weird way over Seattle. And these images, I could see some people smiling and kind of laughing. That's good. They actually were cherry picked to be quite obvious. So like I had a bunch of students I was working with, we made a whole suite of these, and then we were picking the ones that looked as crazy and obvious as we possibly could. And so what we would do is we just bring in a new set of people, same exact task as before, still that face detection task in the middle, except now the last image isn't scrambled. The last image is, you know, part of, I think that's maybe Cambridge in some prison or something, you know, really kind of weird, inconsistent periphery sort of situation. So that's what I'm now plotting down here, is this condition that I call inconsistent periphery. And again, the higher up this bar goes, the more people do not notice. So I thought very naively at the time that this was going to be super obvious. It was going to be totally crazy to people. The, you know, the luminance, the contrast is often wildly different between the center and the periphery. But in fact, actually, this was a little bit harder for people to notice. So people were more likely to notice those major scrambled ones than they were to notice these inconsistent periphery ones. And so just to give you a sense of it again, you know, basically what I'm showing you here is that approximately, you know, 3/4 of my participants did not realize that this was the last image they saw, or that this was the last image they saw, or they, you know, this is the last image they saw. So here's like, you know, 4 examples, 3 of these individuals, 3 of these images, people did not notice that there was anything weird whatsoever. They thought it was a totally normal image with a baby in the middle, okay? So at this point I was like, ah, geez, like, all right, I've taken multiple swings now to try to get, you know, the inattentional blindness rate really low down here. For, like, whatever, let's go all the way. What if there's just nothing in the periphery? Like, what if we just take an image and we just make it gray in the periphery, okay? So you don't see anything out there, it totally goes blank. And in this case, you know, every other image, of course, has stuff in the middle of it. And then it's only until this one that things go blank. Like, hopefully we'll get a pretty big drop there. So now I'm showing this blank periphery condition down here. And okay, yeah, sure. In that situation, now we get a pretty big drop. I don't really know how to explain why this isn't 0. A couple people still didn't notice that we did something odd. Maybe they were stressed out. They want to do a good job on the task. Okay, but we see a pretty sizable jump down here, okay? And what this suggests is like, all right, well, this is good. This is informative. This helps us, because it suggests that there needs to be something in the periphery, or people will notice, okay? If you totally remove everything, then in that situation, people will spontaneously be like, yeah, you made the rest of it gray. They need something to be in the periphery. Okay, but what counts as something? Because what we could find is like, sometimes this is satisfying to people. That's all the image they need. Sometimes this is satisfying people. And by satisfying, I just mean like, they don't notice anything odd if they see this sort of stuff in the periphery. But what if we make it like a completely non-natural abstract periphery that has statistics and images that are in no way indicative of the natural world? So for example, here, you know, a little girl on these, I don't know, bowling balls, this little spiral, these really big spirals, this sort of star pattern, black and white circles. So really high contrast things in the periphery. What happens in a situation like that? Well, what happens in a situation like that is, again, that's really, really low as well. Okay, a little bit higher than the blank, but these two actually are not different from one another. So it seems as if, you know, from a big drop like this, that so long as you preserve natural image statistics in some form or the other, with, you know, either an image that is consistent with the original or inconsistent with the image, that will be enough for people to be satisfied into believing that they must have been looking at a normal image. And at first blush, what I just want to say is that I think that these results are just suggesting to us that a snapshot of perception is remarkably impoverished, actually. But I really want to emphasize this when you're attending to something at fixation. And I think this gets at the question that someone was just asking a second ago. Because another natural thing is like, well, what if your attention is more broadly distributed, okay? Because with this old task, what I did is I was asking you about something at fixation. I was asking you, did the last image have something of human face in the middle? So then what we wanted to do is we wanted to think about, okay, well, what's another natural vision task that people do where their attention will be more broadly distributed. We didn't want to exactly tell people we were going to alter them. We just wanted to make it a little more ecologically valid. And so the new test that we came up with was, rather than ask people about a face in the middle, we asked them, was the last image of an indoor scene or an outdoor scene? And so, for example, we would show them like, hey, these are a bunch of example targets of what an indoor scene looks like. Here are a bunch of example targets of what an outdoor scene looks like. And we did the exact same task, exact same procedures, exact same stimuli, exact same everything. The only thing that changed was the last question we would ask you wasn't if the last scene had a face in the middle. It was just, okay, was it an indoor scene or an outdoor scene? Okay. In this case, just for the sake of time, we only had two types of critical trials, which were the medium scramble condition and the inconsistent periphery condition. Okay. So before I show you the results, let me orient you to this bar graph. So again, the vertical axis is how often people do not notice. We're going to do it for the medium scramble condition and the inconsistent scramble condition. And then down here, this is the original data I showed you from the face task. And then this stuff over here will be the new data. So I've already shown you that for the medium scramble, 50% of people notice it when they're looking for a face. But in this situation, when they do the indoor-outdoor task, it drops down to 15%. For the inconsistent periphery, I already showed you before that about 3/4 of people don't notice it when it's an inconsistent periphery. And then when you are doing this indoor-outdoor task, it drops down by about 30% to about 45%. I'm still pretty surprised, actually, that about half of people didn't notice. Okay, so I really want to.
Excuse me.
Yeah, sure.
When it's an inconsistent periphery, is it from a different scene category? Would it be an indoor periphery surrounding an outdoor center, or what?
It actually could be like a pretty even combination of either. So you could sometimes get a situation of like an indoor dog and an indoor inconsistent periphery. You could get an indoor baby and an outdoor situation. So it was really mixed and matched in all these different ways. So indoor, outdoor to outdoor, indoor and outdoor, and so on and so forth. So when you're seeing something like this is just combining over all those conditions. And we didn't really find any, we looked for a pattern between something like that, like maybe two indoor scenes are harder to notice than an indoor and an outdoor scene combined together. We actually didn't find much data for that. My guess is if there is an effect, it's smaller. And again, we just didn't have the power to do that. But yeah, in this case, it didn't really make a difference. Okay, so I do really, really want to emphasize this point. And I think this is important actually for consciousness research in general, because this idea about the richness of perception can vary substantially as a function of attention. I think that is a very important thing that I haven't done as good a job of always taking into account the function of attention as I should. I actually really think that sometimes when people are talking about their intuitions about how rich perception is, they're having two different conversations because they might be imagining conscious or attention is distributed in somewhat different ways. And so, in terms of asking the question of what is the resolution of perception, there's not going to be one answer. It's going to be what is the resolution of perception as a function of attention. And so what I just really want to make sure to hammer home is that while I think it's very, it's the case, I think this data at least is suggesting that perception is relatively limited. It's relatively limited, but there is some fluctuation with it as a function of the task you're doing. And there are any number of tasks we could do. I'll even show you some different tasks when I get to the VR point. For sure. So once we were in.
Can I ask another question, please?
Yeah, of course. Thank you.
Thank you. It's fascinating. Did you ever try to look into individual differences, so to see what differentiates those who notice from those who don't notice? I know that for the gorilla, they didn't find many. Is it consistent, within individual over time? Is it correlated with any other characteristics?
We haven't done that in great depth. In part, we were discouraged because I know that, like you were just alluding to, they haven't found really strong effects. We did do that in the VR part because we did have the same subjects do a couple different tasks. But even then, it's hard to find strong data because with something like inattentional blindness data, you either classify someone as like a 1 or a 0. It's a binary. You either saw it or you didn't. So finding that sort of trend has been a little difficult. We've seen a little fluctuation of it in the VR. I can try to remember to explain it there, but that's actually something we've been doing with COVID, the lab shut down. So we've been doing stuff on Mechanical Turk, which we're looking into that stuff now. But as of right now, I don't have a great sense of what it is. My honest guess is it is a function of attention, because I don't know how to describe this. This is super not scientific what I'm about to say, but there would just be times in the lab where like it would be like a first year student. They'd never done a psychology study. They were really nervous. You could tell that they were trying really hard. When they answered it wrong, they're like, oh my gosh, I'm so sorry. I messed up, you know? And I'd be like, okay, yeah, this person's not going to notice because they're so focused on the task that they're stressed out. Other times, like, I would come in and be like, yeah, what's up? Like, how you doing? Sitting back in his chair. And I'd be like, yeah, he'll probably see it because he's like, yeah, you know, his attention, his mind is wandering. So for what it's worth, that's about as much as I can say right now. I think I saw another hand. Was there another question?
I had just a very quick question. Maybe I was just wondering the effect of expectation versus attention, because I think these processes, we know they are different actually, at least from the neural and also behavioral point of view actually.
Mm-hmm.
So do you think there could be a little bit of a confound of, because obviously you must be telling them, okay, what type of image probably you will be looking for, or at the end you'll be reporting. So that kind of like expectation comes in here as well.
Okay.
So I'm just wondering, you thought about the any confounding effect of these two processes?
I don't think it's necessarily a confounding effect, but I will say this. I almost want to punt on this because I think that this issue about expectation, I've become in my own little way convinced that this matters so much for explaining like these illusions and these failures of awareness. And so at the end of it, I'll even like give a reference to, you know, Bayesian inference and this role of how you have these priors and these beliefs and these expectations of what the world's going to look like. I think that plays a crucial role. But maybe I can just show you guys a few more results before we get to that, because I think that will ground the discussion a little bit. But I'm 100% with you. I think that's a very important factor, though I don't know if I would necessarily say it's a confound as much as it is just like a variable that we need to account for in consciousness research.
Sure, thank you.
Okay. So the next thing that we did want to know is about how rich your color perception is in particular. So rather than just talking about natural scene statistics, what about color in general? Because obviously the world is not in black and white, the world is in color. And rather than kind of do these things simultaneously, we did a sort of divide and conquer approach. So what I'm going to tell you about now is the same exact paradigm, same exact everything, the same face task. We've changed nothing. The only thing that's changing now is the images are colorful. So I'll just show you an example of what a stream like that looks like. So again, tell me if there's a face in the middle in the last image. So a bunch of super bright, super high contrast images, actually brighter than what the natural world looks like. You know, you'd say, what's the last image of face? Here, we'll do one more. So really, really rich images. And then all that would happen is on the very last trial, what we would do is we would just simply desaturate the periphery entirely. So for example, a man like this, the world would start to look like this, completely black and white. A little girl like that, again, the world would become entirely black and white. A very colorful restaurant, and again, the world would become black and white. And so it's just a wide variety of fantastical and wild scenes, sometimes, you know, not really realistic, sometimes super realistic. Any of these images could become black and white. And again, I really want to make sure to emphasize this point. These images were super saturated. So it is not like we took cold, dark, gray, dreary days. We actually did some analyses of these images, and it turns out actually that if you look at what the overall saturation is of our stimulus set, they were far more saturated than actually what people see in most everyday life. So we were actually kind of biasing it against us and by making them so saturated. So one situation we had was when we desaturate the periphery. The other is not just desaturating it, but color rotating the periphery. So you could take something like an image like this, and rather than make it black and white, you can rotate the image in terms of the color wheel. You can take something like this, you know, peacock logo, and again, you rotate it. And so it gives you a lot of really kind of altered looking weird images that you might not expect. For example, I didn't really know this, but you know, if you take this, I guess I should have known this from the daylight axis. If you take this image that has a lot of orange with these rocks and you rotate it, they become blue. So then the target image, because we would preserve the middle part of it, is normal. And then the periphery is all blue skin, blue rocks, kind of an orangish sky, although it's pretty desaturated. In this case, greens will become purple, where this man's face stays normal, and then all the flowers become purple, although his arm is a weird kind of color. And then again, you've seen this one where this mermaid, the color in the periphery becomes this sort of pinkish, reddish type of thing. Okay. So this again, hopefully it's pretty straightforward because it's the same sort of vertical axis here in terms of the rate of not noticing what we changed, when in this case we desaturated the periphery and made a grayscale versus when we rotated it. And in this case, 70% of people did not notice when it was black and white, and 75% of people did not notice when it was a color rotated periphery. This was kind of interesting. I was hoping, I thought it would have been kind of cool and interesting if there was a difference, because then maybe there would have been something about like, you know, if this was significantly higher, it would have been like, oh, when there's some color, that's enough to satisfy your expectations of seeing a colorful world and so on and so forth. But actually, it just sort of seems like by and large, people don't notice what's going on in the periphery in this domain, because if it's grayscale or if it's rotated, people are none the wiser. And so again, these results suggest that at least a single snapshot of perception is not especially colorful. But again, this is when you are attending to something at fixation. So then once again, how do these results vary as a function of attention? So then we did the same thing we did before, the rate of not noticing for these two desaturated rotated conditions as a function of the different tasks. So I just showed you this result here that you would not notice it 70% of the time. When you're doing an indoor-outdoor task, that comes down to 33% of the time. And then again, when it's 75% of the time, 3/4 of people are rotated, 3/4 of people don't notice it. But when they're doing the indoor outdoor, it does start to, they can notice it significantly more. Still pretty low though. So the resolution of color perception certainly increases when attention is distributed more broadly. But I do want to emphasize this one point. I was still pretty surprised that it's really rather bad, even when you are kind of attending to the periphery. I mean, you know, I've got these really kind of wild psychedelic images where, you know, it's topsy-turvy, blue becomes orange and so on and so forth. But like, you know, almost half of my people still don't notice, or I remove all the color from the vast majority of the image and 1 out of 3 people don't notice. I was pretty shocked by that. I really thought these numbers would even get lower. And so it was at this particular time of doing these studies, once we kind of got this data, where we kept kind of like running into this thing about like this knob and like, what is the right task? Is this face task a good task? Maybe it shouldn't have been a detection task. Maybe it should have been an identification task. Is the indoor outdoor task do what we want? We had all these conversations about what is the right task. And so then we tried to think about like, well, what if you weren't looking at a screen doing an artificial task at all? Like, what if we just were like, you know what, forget it. We're just going to try to make this as natural as we can. We're going to try to like, how can we put people in the real world and let them interact with the stimuli in a way that is natural to them? And to do that, that's how we kind of got to thinking about using VR. Because what we wanted to do in this situation here is we're like, all right, let's put people in a headset. And what we're going to do is we're going to just let them look around. We're going to give them no task whatsoever. So if you were a participant who came in to do the study and we put you in the headset, we basically, I don't want to say we would lie to you, but we're like, this is a study about real world perception. What we're going to do is we're going to put you in this virtual world, and just whenever you're there for about 20 seconds or so, just look around however you want. It's kind of fun. Pretend that you're like meeting a friend there and you're just killing time until they show up. You know, you can do whatever you want. There's no task. And the participants would be like, wait, really? Like, there's no task? Like, no, just look around. We're going to ask you some questions later. But, you know, I don't know if you've ever done VR. It's kind of fun. So yeah, you know, have a good time. And they're like, okay. And so what we would do is, again, excuse me, is in this case, what we now did was change the parts of the world that they are not directly looking at. And so this was completely inspired by studies that have been done from eye tracking and creating gaze contingent displays, except in this situation, rather than have an eye tracker that would, you know, be on your desktop underneath your monitor, we actually embedded eye trackers into the headset. And so when you were a participant putting it on, you could actually see there were these little cameras underneath the two like windows with which you'd see the world, and they're the things that are tracking your eyes in real time. And there's already been a bunch of studies, of course, that have happened using gaze contingent viewing. The most famous, I think, come from reading, because starting, I think, back in the 70s, Keith Rayner in the US started doing these studies where he would basically at one moment to the next be tracking where is a person looking while they're reading. So at time point 1, you're looking at the word while, then you're looking at the word your, then you're looking at the word most. And what he found, which I've always thought is an underratedly cool result, is that if you change basically all the other letters in the lines, except the ones you're fixating at, to X's, you basically can't notice that they're X's at all. And so as you're moving, it's this kind of gaze contingent little dynamic window where everything in the periphery is just, X's, and only that one word is a real world. Real fun little anecdote. When I was an undergrad working with Dan Dennett, someone came to do a demonstration of this for us, and as a joke, we didn't do X's and X's and X's. We just did Dan Dennett, Dan Dennett, Dan Dennett, Dan Dennett, Dan Dennett. So everything on the page was Dan Dennett, and he just saw one word and he was completely oblivious to it. So long as you keep, letters there and they're horizontal and so forth, people won't notice. However, if you remove all the other letters, that people will notice. Like as soon as you do something like this and you only see one word at a time, that pops out immediately, because presumably something like, wait, you're no longer looking at a page of words, you're just looking at a blank page. So we're basically going to use a procedure kind of like this, but like I said, we're going to do it in a virtual reality situation while people are looking around the world. And then the last thing I'll say is that we also gave people dynamic audio visual stimuli here, again, because we were so focused on trying to get you to real world perception that it wouldn't just be one static image, it would be a dynamic movie where you would actually even hear things. So our headset is equipped with these headphones so that you could actually hear things going on around you. So before we get to the actual experiment, let me just try to give you a sense of what it was like in the headset. I apologize if this is laggy. I apologize if the audio doesn't work. You'll have to just kind of take my word for it that what we did was smooth and high resolution and so on and so forth. But let's see if this works. And then, yeah, there we go. So this is a participant looking around the room. And as you can see, he's got no task. He's just kind of having a good time. And this is what it looks like from his perspective.
My name is Chris Sussens. I'm the manager or ranger here on Chukudu Wildlife Reserve. We're in a very severe drought at the moment, so that's why we're actually feeding these.
All right, so that was one example, a guy looking at rhinos. We'll do another example.
We have underway, we're making a bunch of dummies to collect shrapnel from a blast. And we also have our spray booth, or the area that we do spray painting or vent fumes. And there's the famous wall of boxes. The boxes have just about everything that you can imagine that you could ever want.
Okay, so this was obviously where people were saccading. They're kind of looking, hopefully, in what looked to you like naturalistic places. They were looking at the faces. They were looking at the wall that the guy was talking about. So wide variety of different sort of stimuli. And then again, we would do this sort of like one critical trial manipulation. And in this case, what I'm going to tell you about now is just going to stay in the domain of color, where what we would do is desaturate the periphery in this gaze contingent manner. So it's almost like a colorful window that's moving around with your eyes while the rest of the world is totally in black and white. So to give you a sense of what I mean, this here is intended to be a visualization of the world, what the world looks like to you. So if this sort of odd shape here, this is what your right eye sees, and then this is what your left eye sees. This is the part in the middle that both eyes see, that's the overlap. And we had a bunch of conditions, and this is just to try to give you a sense of what those conditions were. The largest condition, when it was 32.5 degree radius, we would keep this part of the world in color, and then the rest of this would go into black and white. Then we had a 25 condition, a 17.5 condition, and a 10%. So it's getting smaller and smaller and smaller. If you're not entirely sure what exactly I'm visualizing here, that's okay. Let me try to show you this same sort of idea in a different way. Now let's imagine I'm looking at you from the top. It would almost be the equivalent of a 32.5 degree is sort of like a window like this. If this is 180 degrees around you, then the 25 degree condition, the 17.5, and the 10 degree. So the 10 degree condition, it's really, really rather short. If you hold, to give a really good sense of intuition, if you were to hold your arms straight in front of you, I don't know if you all can see me in the little thing, but if you hold your arms straight in front of you, the size of this window is about 8 inches across. Gosh, I just remember 60. I don't know how many centimeters that is. About 20 centimeters, actually. Yeah, that's right. It's 20 centimeters. So 20 centimeters across at arm's length, that's how much you're going to see color. So it's a really small amount of color. It's not like I'm doing it for a huge amount. It's really just, 20 centimeters and so on and so forth. So what I'm going to do is I'm going to show you when we desaturate the periphery and only maintain this part of it here, how often do people not notice the desaturation as a function of the size of these different windows, okay? But before I show you the data, let me show you what a critical trial looks like. So let's start over here on the right. I'll show you one of the largest conditions, okay? So in this video, I want you to just take note before I start it. Right now, it is fully desaturated, and after about 7 seconds, it will desaturate, and then once it desaturates, it will stay desaturated, and hopefully you'll get a sense of the dynamics of what it looks like. So let's try this out.
But this is the hobbit hole. This is the main one. It's got the best view as well, I think. See if you can have a little peek inside.
Okay, again, because it's Zoom and I don't know how laggy it is, I thought I would just show one screenshot. So this, for example, would be like what the world looks like to a participant when they're looking at this pumpkin. This stuff is in color, and then the periphery is in black and white. And hopefully you at least saw that it was a dynamic, moving kind of circular aperture that would move as a function of where the person was fixating. Okay, so in this situation, the vast majority of people did not notice that we did anything at all. Only a handful of people did. But overwhelmingly, people were like, sorry, no, I didn't see anything odd like that. I didn't notice anything in the periphery. We could even tell them or show them the effect that we did and show them what we did in the periphery. And they'd be like, wow, you did that? I completely didn't notice it. Okay, so what if we make it a little bit smaller? Here's another video.
Howdy, I'm Brian. I'm Justin. And we're checking out the best parts of Austin here with Discovery VR. And when they say keep Austin weird, I'm 99% certain they mean this place.
We are in suburbia. Family-friendly home, and then we pull in here to see one of the most amazing structures I've ever borne with.
And so again, just to give you a sense of what one image looks like, now you can see that this colored regions are getting a little bit smaller. And so then in this situation, it drops down from 83, still at 65, still, 2/3 of people, more or less, don't notice that we did anything odd. Okay, let's see the two more videos conditions.
I wanted to show you guys what's new this year. This year's focus was to try to get more product through our plant. We knew to get to 2,700 ounces, we had to run this thing pretty hard. And our biggest problem last year was our tailings. If you look way down there, you see big piles of gray rock. That was all of our tailings. So it took a lot of...
Okay, one more screenshot. So you can see now it's really getting rather small. So in this situation here, it would be about 35 centimeters at arm's length. So now we're really getting pretty tiny. This was the 50-50 threshold. Now half the people noticed and half the people didn't. And now let's just round it out. Do pay attention to this video. This video is my favorite.
What is a highlight, but we don't even know what it is. What is a highlight? Highlight is the world's fastest sport. How fast does it go? 180 miles. That is fast. All right, how do I fling the ball so it goes that fast? All you have to do is keep your wrist loose all the time and throw the ball to the front wall. So it's similar to racquetball or squash? Yeah, kind of, but fast.
Okay, I should have just mentioned something I didn't before, which is this here is an actual still from a person who did not notice it. So the video I was just showing you, and this image here, this is the person who is subsequently going to say like, wait, you all made it black and white? I had no idea. Okay, so it's a really small bit of color, and the vast majority of it is in black and white. But in this situation, this is a case of someone who didn't notice. And in this situation here, it's a nice, oh gosh, it's a nice pseudo linear trend here. It goes down to 30%. But I am a little bit more of a glass half full kind of guy, I guess, because to me, I'm like, wait, 30% of people didn't notice that? Like 1 out of 3 participants could look at the world for several seconds like this and not realize that the periphery is completely desaturated. To me, that was really surprising. And the fact this is even more surprising when you can remember that there are no tasks whatsoever. It is natural attention. It is as close to real world viewing as I think is actually conceivably possible. We're letting people do what they normally do. So we're not doing any sort of top-down manipulation. This is just as close as we can get to a reflection of what the world really looks like for them. But we did want to know, and just kind of as a sanity check, okay, well, what if people do distribute their attention and are looking for the desaturation? Like, what if we really just tell people, hey, we're going to do this, look into the periphery, see if you notice it. And so, and then in that situation, what we wanted to do is we wanted to get a sense of like, what are the outer limits in this case? So we did this sort of thresholding procedure where across several trials, we would change the size of the colored region as a function of if people notice it. So if on the first trial, we start with the radius, it's like 45 degrees. If our participants say, yeah, I could not tell that there was anything changing there, sorry, I didn't notice it, we'd be like, okay, let's change it a little bit more. And then as they do notice it, we alter it and go on and so forth. And we basically keep making the colored region bigger or smaller until we find like the 50-50 mark where they're completely at threshold. So what I'm plotting here is what does the color radius have to be? How big does it have to be for people to not notice it or for people to be at chance, okay? So here are actual, are 20 of our participants. So for each one of these participants, it's like, okay, for this person, it actually could be really small before they notice. For this person, it could actually be really rather large before they notice. On average, it's about 37, 38 degrees. To give you a sort of an intuition of what 37 or 38 degrees is like, if again, this is your full field of view, this is what 37.5 degrees looks like. So it's still, you know, not your entire field of view. It's still, you know, I don't know, 30, 40, 50% of it. Relative to you as a person, 37.5 degrees is this orange bar out here, where then just to give you a point of comparison, these are these colored ones here. So this is bigger than any of the inattentional blindness conditions that we had, but it's still by no means going all the way out into the periphery, at least as of now. So then to oh yeah, go for it.
I mean, if you did this by old-fashioned psychophysics, looking at color discrimination with eccentricity, I mean, you know, cone density falls off rapidly. What do you have any idea what those figures would be like?
Those figures would be sharper than this in the sense that the cone density drops off faster than this sort of image is. So it's not as if this 37.5 degrees, you know, we all see in like a sensation and perception textbook, those sort of like visualizations of the fovea where the, you know, the cones drop off are like really high in the center and they drop off really quickly into the periphery. Like this is a wider distribution than that. And we think that
but I'm asking if somebody actually did the experiment of, you know, fixating centrally, making a saturation discrimination of some kind, 30, 40 degrees out. Do you have any idea what those data look like?
Yeah, you can do some of those actually. Like you could have a dot, like a red circle or a blue circle in the periphery and tell those apart. But the reason that I don't think that those are necessarily reflecting perception in everyday life is that A, things are usually very crowded in the real world. Like usually you don't see a thing in isolation that's that saturated. And then B, your attention is usually not going all the way into the periphery. So for us here, what we were trying to do is not map out the outer limits in a perfectly controlled psychophysical situation.
I understand that, but that data should be setting a kind of limit. That is, there's a point at which your experiment isn't interesting because you're actually just up against this basic psychophysical limit. And I just wonder how far you are from that.
That limit is pretty far out, actually. Like if you take a big like beach ball and you put it in your periphery and it's one solid color red, like you can have stuff really pretty far out there. If it's not cluttered, if it's saturated enough, if it's not crowded, if you're attending out there, yeah, you can get further than this here. But what we're just trying to say is that when you're in natural scenes, when you have your attention naturally distributed, because at least for me personally, I'm kind of interested in like understanding the phenomenology of everyday life. That's what we're kind of focusing on here. And so that's why I even say on this slide, in everyday life, because I'm focusing on that, your visual experience, at least I would argue, is shockingly less colorful than it might intuitively seem. And just to kind of wrap up real quick, I would say that actually taken together, overall, what these studies suggest is that your experience, I at least would argue, is much less rich than it intuitively seemed. The question, though, of course, that I am now very focused on, and I don't think as a field we have a great answer to, is like, well, why doesn't it seem that way? So why isn't it the case that people, like, you know, you might think like, yeah, we're going to find these results. This is a form of like, you know, inattentional blindness, as it were. So what are the different factors and mechanisms that are preventing people from, you know, having this intuitive sense that the world might be as sparse, as it were? I just realized this animation isn't right. I apologize for a second. But here are some future directions that we've been working on lately. So one big one that we've been working on is familiarity, because perhaps there are different rates of noticing when it's a scene you remember or you are familiar with. So we've been doing stuff now where we don't show people novel new worlds that they're trying to like build up a representation for. We do experiments like this where it's scenes that people are highly familiar with, because, you know, like right now I'm sitting in my office in our building, and it's like, this is a room I know very well. This is a room that I'm extremely familiar with. All the objects are where I want them to be. And so what are the rates going to be like? Because perhaps one thing that's going on is my brain, to a certain extent, might be filling in colors that, you know, I have a red bowl on my desk next to my monitor. Perhaps my brain is actually kind of maintaining that representation, even if it's not coming in through the sensory system. Another possibility, and someone brought this up a little bit ago, is this idea of the illusion of rich perception as a product of Bayesian inference. I really think that there's a really good chance that what's going on is that, like, in everyday life, you're like, the world is in color and the world is in high resolution in the periphery. Like, the world doesn't change when I look around. And so you have this really, really strong prior belief, this expectation, in other words, that the world is in color and that the world has all of its detail. And so I think that to notice that we have done these weird things, you have to have a really strong signal to update that prior or to change that expectation. And I think that there could be some interesting work to be done about, well, what if people go into a situation with a different expectation or a different understanding of the world? They're going to maybe notice things at a different rate because they don't bring that sort of prior belief or prior expectation into it. If there are other ideas that people have about why we feel like we can see so much more than this data suggests, I'd love to hear what other people's intuitions are to account for what is the reasons that I can, change so much of the world without people noticing. So I'm hoping people have some questions or ideas. I just want to give a quick thanks to some of my students and colleagues at Amherst that I've worked with. Also, I really want to give a special thanks to this woman right here, Professor Caroline Robertson, who works at Dartmouth College in the United States. She runs a VR lab. It's through her infrastructure that we've been able to do this VR stuff, because it's her expertise in that domain that I just kind of piggybacked on. So definitely I want to give a shout out to my colleagues there. And then thanks to all of you. And I'd be happy to take any questions you have.
Awesome. Let's quickly unmute ourselves and give a big applause. So let me just stop the recording.